Hello everyone, now we're going to look at the application of ideal gas law and Dalton's law in the famous type of question in exams for matriculation, um, water displacement method. Okay, so this is one of the question that students might gonna find a little bit more challenging, but to tell you the truth, it's not that difficult as long as you would be able to know what's going on in terms of the concepts and how we're going to apply Dalton's law and also PV equals to nRT into solving the questions about water displacement method. Okay, so the first thing we need to look at is we need to be able to imagine how is the setup for this kind of experiment. So what you are looking at now on your screen, this is a very typical diagram of how we're going to conduct the experiment typically in your lab. We can do this with different kind of method if you want to. Even you can do this in your kitchen or in your room, provided you have the correct equipment. Okay, so what you see over here, what we're going to be doing in this experiment, we have the part where you're going to have the reactions going to happen. So the reactions that is happening in here will produce gases. Okay, so maybe it's going to produce hydrogen gas or maybe oxygen gas. Okay, so in your syllabus, usually they can use oxygen gas, O2, or maybe they can use hydrogen gas. Okay, so whatever gas they're going to use, what happened now is when the gas is released from this reaction here, the gas particle will travel along the tube. Okay, and then they're going to start to go up here, and then the gas particles will get into that part of the test tubes. Okay, so what you need to remember now, you have water over here. Okay, and then you do know that liquid water, H2O, it has its own molecules. Okay, so when the gas particles, the gas molecules that is being produced here, travel along this tube and goes out from that end, when the gas particle tries to go up, it will start to push the H2O molecules along with them. And therefore, inside here, what you get is the gas particles together with the H2O gas molecules. Okay, so that is the typical concept you need to know before you would be able to do the calculation for water displacement method. Okay, so let's have a look at another diagram. Maybe this one will be a little bit more realistic looking. This is another setup. Okay, so instead of having maybe two solutions mixing together, you can have a solid, like over here you have that solid, and then you heat that up with a button burner, and that heating up process will cause the reactions over here to produce oxygen gas. So oxygen gas will be produced, and the oxygen gas particle will travel along this tube again. So as you can see, you have bubbles over there. Those bubbles are oxygen gas. So when those oxygen gas molecule tries to go up to get into that area, it will start to push the H2O molecule along with it. Okay, so the H2O molecules that you have inside the liquid will be pushed by the oxygen molecule, and together they will exist in that part of that chamber. Okay, so when we're gonna try to work out question regarding to water displacement methods, the P total, you need to remember, will always gonna be P, the partial pressure of the gas, whatever gas is being produced at that end, plus the partial pressure of your water vapor. Okay, so that is a very important concept. Let's have a look at another diagram. So this one is a little bit more detailed. So what I was trying to say just now, so this is another different kind of reactions. You have a solution over here, and then you have dissolved zinc, and then because of that reaction between the HCl and the zinc, H2 gas is being produced. So all of these, what you see here, those are H2 molecules. So when those H2 molecules are traveling down, going upward to that end of that tube, you can see that bubble gas. Okay, so those here are H2O molecules in the phase of liquid. So when your H2 molecules going up, what happened? That molecule will be able to push the water molecule to go out with them to become gas. So that is why whatever you have in here, this is what you call the atmosphere. This is going to be the pressure total, because it will be the partial pressure of H2 gas plus partial pressure of water. Okay, so this is basically the concept that you need to get into your head and then try to imagine it every single time you have questions about water displacement method, okay, to collect gas. So let's have a look at example questions. Over here, it's very obvious. The question is telling you that this is indeed a water displacement method. So when it says that, automatically you need to remind yourself, you need to get the pressure of the gas, okay, by considering the P total minus the partial pressure of the water vapor. Okay, so what we have over here, it wants you to find out this. You want to calculate the mass of oxygen gas being obtained. So that is what the question wants. So the question wants, okay, what is the mass of oxygen gas obtained? So when we want to find mass, okay, so when we want to find mass over here, what we need to consider now is the number of mole of O2. Okay, because so far in the states of matter, there is no formula that you can use to get mass directly. But what you use now is PV equals to nRT, and in that formula you have mole n. Okay, why do we need to think about mole every single time the question wants you to find mass? Okay, so this is a very good tip. Every single time the question wants you to find mass, think about mole. Okay, the reason is because if you go all the way back to the MAMOVONO tree, okay, to get mass over here, as you can see, you need to get the number of mole first. When you get the number of mole, you can work that out with the molar mass of the species, and you will multiply with the number of mole, and therefore you would be able to get the mass of the species. Okay? So as you realize now, this chapter is very related to the earlier chapter that we have done before, chapter 1. Okay, so we have looked at MAMOVONO Tree before. Okay, MAMOVONO Tree. So from this MAMOVONO Tree, you would be able to get an idea of what you need to do next. Okay, so let's go back to this question. So now our task is to find the number of mole of oxygen. Okay, so that is what the question wants. What about what the question gives? So the question gives, so it's very important for us to extract information. So by doing the extracting of information, you would be able to know what sort of formula you need to use. Either you need to use PV equals to nRT, or maybe you need to use Charles's law, or maybe you want to use Boyle's law instead. So everything will be quite clear. You will know what you need to use when you start to extract all the information. So over here, when I extract the information, I know that we have the volume of oxygen gas, which is right over here. So that is 128 mil. And we know that when you see ml, if you want to use this for PV equals to nRT, we need to change that into liter. Okay? And then what else? We have temperature. Okay, so the temperature is also given to you. It's right over there, temperature. So 24 degrees Celsius. And then we have atmospheric pressure. Okay, so that is the pressure that we need to consider. Okay, we need to consider the pressure. So the pressure, so this is, when it says atmospheric pressure over here, that is your P total. Okay, so that one should be your P total. So your P total is 762 millimeter mercury. So when you look at millimeter mercury, you know that we need to do some conversion. Okay, so we have all of this information, and then we need to find the number of mole. We have PVTN. So what do we need to use? Of course, we need to use PV equals to nRT. But then again, we need to get, okay, the pressure for oxygen. So how do we do that? Okay, because this is water displacement method, remember? So when you have P total right over here, this P total is the combination between the partial pressure of oxygen gas and also H2O. So the partial pressure of O2 is going to be P total minus partial pressure of the water vapor. So you have to remember this. Always remember this for water displacement. Okay, so the P partial pressure of oxygen is going to be 762 millimeter mercury minus what you have here. If you read further down the sentence, you have the vapor pressure of water is 24 millimeter mercury. So you minus with that one. and you get 7.38 millimeter mercury. Okay, so now we have all the information needed. What do we need to do now? We just need to do the conversion first before we can use PV equals to nRT to find our number of mole of gas. Okay, so now we're gonna do some conversion. So we're gonna do millimeter mercury to ATM. So how do we do that? 760 millimeter mercury is equivalent to 1 ATM, and the partial pressure of oxygen is 738 millimeter mercury, and we need to find that. Okay, so we have done this before. You go here, you times, and then you go up, you're going to divide, and that one should be, the value is going to be about 0.971 ATM. So this one is for the partial pressure of your oxygen. Okay, and then now what we need to do, we have to find the convert also okay, so we have ml, we convert to liter. This one is quite easy. You have 128 mil over 1000, you get 0.128 liter. And then the next conversion is for the temperature. Okay, so from degrees Celsius we need to convert to Kelvin. We have 24 degrees Celsius plus 273.15, then you get 297.15 Kelvin. Okay, so we take all of this value here, we're going to substitute to here, PV equals to nRT. Okay, so when you rearrange this, you get N for oxygen we're going to find over partial pressure of oxygen, volume over RT. Okay, so the partial pressure just now we have 0.971 ATM, and the volume is about 0.128 liter, and the value of R is 0.0821 liter atmospheric pressure per mole per Kelvin, and the temperature is 297.15 Kelvin. Okay, so we can cancel that, and then we can cancel this one and that one, this one and that one. So the number of mole of oxygen should be about 5.095 times 10 to the power of -3 mole. Okay, so now we're going to change this number of mole into mass. How do you do that? Okay, so mass of oxygen obtained is, just now we have 5.095 times 10 to the power of negative 3 mole. So if you go back to your MAMOVONO tree, you have your mole over here. To get to mass, you have to times with molar mass. Okay, so the molar mass of so that is the molar mass of oxygen. So when you times with that one, you should be able to get 0.163 grams of oxygen. So now we're going to have a look at this example. Okay, what about the second example over here? How do we do this? For the second example, as usual, we need to find out what does the question wants. Okay, so the question wants you to find this. What is the volume of the dry gas at STP? So we need to find that one. We need to find the volume of the gas at standard temperature and pressure. Okay, so at standard temperature and pressure, the pressure would be 1 atm and the temperature would be 273.15 Kelvin. Okay, so we can use PV equals to nRT to find the volume, because over here we have the pressure, we have the temperature, but what we don't know is this. We don't know what is the number of mole of the gas. Okay, we want to find this too, but we need to figure out what is the number of mole of the gas. So how do we do that? The question gives, the question gives information about volume of the gas at 26 degrees Celsius is equals to 325 mil. Okay, so here what you can see, you have your volume, so that is the volume given to you. You have your temperature, okay, and what can we do is we can also find the pressure of the gas. And how do we do that? Because when you look at the question here, you have the word gas collected over water. So this is also water displacement method. When you see clue like this, that means you need to consider water displacement. So to find the pressure of gas, we need to consider P total minus the partial pressure of the water vapor. So this is water displacement. Okay, so what is the value then? So the pressure of partial pressure of the gas is equals to P total. So the P total given to us is this. Okay, 742 millimeter mercury. And then what is this? It's given to you right over here. Okay, the water vapor pressure is 25 minus 25 millimeter mercury, and therefore the partial pressure of the gas would be 717 millimeter mercury. Now, we have enough information, so that is the pressure. We have P, V, and then we can find N, R is the constant, and then T. Okay, so as you can see, we need to do a bit of a conversion over here before we're going to do anything else. So first thing is we convert millimeter mercury to ATM. So 760 millimeter mercury is equals to 1 ATM. And the partial pressure of the gas is 717 millimeter mercury. And we want to know how much is that in terms of atmospheric pressure. So X ATM is how much? So remember, go across here, you multiply, and then you divide, and you should be getting a number around this 0.9432 atmospheric pressure. So the next thing we need to convert is we need to convert the temperature. Yes, so from degrees Celsius to Kelvin. So what we have 26 degrees Celsius, so plus 273.15, and that is 299.15 Kelvin. Okay, and then next is the volume. So you have milliliter, you convert to liter. So 325 mil over 1000 mil. So over 1000. So you should get 0.325 liter. Okay, so we have converted all of the values into the right units for us to use PV equals to nRT. And now we can proceed to find out what is the, okay, we can use PV equals to nRT now to find N, the mole of gas, so we can rearrange, so the pressure of the gas over RT. Okay, so the number of mole of gas that we want to find, the pressure of the gas just now is 0.9432 atmospheric pressure times with the volume, it's about 0.325. Is it 325? Yes. Liter. And then the R value is 0.0821 liter ATM per mole per Kelvin. And the temperature is 299.15 Kelvin. Okay. So you can cancel liter and liter, atmospheric pressure, Kelvin and Kelvin, and then you have mole. So the number of mole of the gas should be around 0.01248 mole. Okay, so that is very important for you to get. Now, what we need to do now is we need to find out what is the volume at STP. So that is our mission just now. We want to find out what is the volume of gas at standard temperature and pressure. We have the information, we have the pressure, we have the temperature. Now we have the number of mole. Okay. So again, we're gonna use PV equals to nRT again. Okay. So this time we want to find the volume of the gas. So we're gonna use and number of mole of so I'm just gonna go back slightly. Okay, I'm just gonna change something over here. That one is gas. Okay. Okay, so the volume of gas, so that is the mole of your gas times RT over P, pressure. So the pressure at STP, yeah. So when we substitute all of the value inside, we would get 0.01248 mole times 0.0821 liter atmospheric pressure per mole per Kelvin. And over here, so T, remember the T and P now, this one is 273.15 Kelvin. This one is 1 ATM because it wants you to find at STP. We want to find at STP. So your temperature is 273.15 Kelvin. And then your pressure would be 1 ATM. So you would be getting 0.279 liter or 279 milliliter. Okay, so alternatively, what we can do is, if you look at your MAMOVONO tree, there is a shortcut. Okay, so when you have found your number of moles, let's say just now the number of mole is about 0.01248. So I have found that number of mole. So I don't want to use this method. Okay, let's say I don't want to use this method over here. I want to use something else. So let's say the number of mole of the gas just now is 0.01248 mole. I have found that. So without even substituting the value into PV equals to nRT again, I can use this because the question wants you to find at STP. Okay, so when the value wants to be STP, you can use that value here, which is a constant for STP, times with that to get the volume of the gas. Okay, so let's try. So if you have so you're gonna find volume of the gas. I'm gonna take 0.01248 mole times with, I'm gonna do that again. Okay, so the volume of the gas, so 0.01248 mole times with 22.4 liter per mole. Okay, so Mole and mole cancel. So what you get, you're gonna be getting the same answer as well. Okay, so that's another shortcut or alternative.